today's topic will be optimization. Before we begin, any questions from you? We have, or you have, now exercises 5 also out. Exercise 4, I told you, was the one you should pay some put some effort into. You have gotten the solution for exercise 4. Should be out here. Just remember, the solution for exercise 4 is a bunch of execute files that can be run on the window. So if you're having MATLAB or Linux on your machine, then you have to run in a window virtual box or something. Okay. So today then, optimization, preparation for exercise 5. And tomorrow, more examples. We are going then to touch into the topic that is called regulation and control. That will be a little bit for next week also. But today, optimization. No questions from you? It's okay? That is good. So, optimization. What do we mean, optimization? Well, in practice, optimization means we have a function with n parameters as input variables, and we want to sort of find the optimum performance of this function. And always we are talking about minimizing. Strangely enough, always minimizing, never maximizing. You are minimizing what's called a cost function. And this cost function, how do we write it? F of x. Always minimizing. Minimizing the costs, it sounds like some economic principle, and yes, typically this will be based on economics. You are to construct a factory or something, you're going to build something, you're going to produce some object, minimize the cost. That's the only important thing with the economics. Minimize the cost, minimize the price. For an engineer, we don't care about how much it costs as long as it works. But for economics, they talk a different language, sadly. So sometimes, yes, we have to try to understand what they are talking about. So minimizing a cost function. And the whole idea with optimization, the job with optimization will typically be finding this cost function, or sort of construct this cost function. This x here, in general, x can be as many variables as you want. It doesn't have to be just one. It can be many variables. So you have x1, x2, yada yada, xn. So it can be many. You're talking multivariable functions here. If x is 1 or maybe 2 parameters, then this is not a big deal at all. But when n becomes 3, 4, bigger numbers, it's very difficult indeed. So actually, optimization can be a pretty huge topic. So here we are just going to touch the area. So minimizing a cost function. Let's jump directly to an example. Example, you are to construct a box, say a pool or something, given one sheet of, say, paper. We are going to build this one in a paper. Build a paper box with the biggest possible volume. Let's see, find, actually find x, so that we get biggest volume. So here is your paper. It has length A and width B. Construct a box out of this piece of paper. How do you do that? Well, you take a pair of scissors and then you cut away the corners like this. And then you cut away these 4 corners, and then you fold everything. Maybe I should draw it like this, would be better. Like this. And then you fold it here. So in 3D, you will have something like this. And how big will this box be? Well, the corner have all size x by x, of course. So what is the volume? Volume equals, well, the length now is A minus 2x. The width will be B minus 2x, and the height will of course now be x. So that's the volume. This is my negative cost function. Remember, here I want to find the biggest possible volume. It is to be maximized, but within optimization it's always minimized, sadly. So my cost function will now be a simple function of x. I only have one parameter in this problem. Now will be minus volume. And what will it be? You have a, b, x. You will have minus 2ax minus 2bx plus 4 times x to the power of 3, and this should be actually power of 2. With a negative sign on. So the optimization problem here, find the x that gives me the minimum cost function value, which then evidently is going to be the biggest volume. Everybody with me? Okay. Now we can have something that is called constraints. We have or may have some limitations on our parameters of our input values here. So find the minimal cost function with respect to the different x's, where these x's also have to fulfill some, say we have some non or inequality constraints. And we have equality constraints. Inequality constraints, meaning you have some expressions, some functions, g of x has to be then bigger or equal to 0. For instance, equality constraints, you have a function, say, what did I call it, h of x that has to be now on the form equal to 0. So you may have some constraints, some limitations on your parameters. What about this one? Do we have any limitations on x? Well, clearly we have some physical limitations here. So we will have x definitely has to be bigger than 0. A negative distance makes no real sense. You have an imaginary volume. Also, x has to be smaller than what? It will be the minimum of a half be half, the smallest one of those two. So x has to lie within those boundaries, clearly. So we have two inequality constraints for this problem. No equality constraints. And here, of course, you can have a whole bunch of these, depending on how many variables we have. I mean, like here, we had only one parameter. Still, we have two constraints for him. So here, for each of these different parameters, you can have a set of different functions here that has to be fulfilled as well. It's not always that we have these constraints, but sometimes, yes. It can be physical, it can be logical, it can be, say, you're going to build a bike or something, and then you're going to build a bike of parts that you find in a shop. That is just standard parts. Okay, then you'll just have a set to choose from. You can't have a continuous function. Then you will have some step in these constraints here that either you could use this one or you could use that one. So you sort of have to choose among building parts. Okay, let us see if we can find the solution to this problem here. So what will the solution here be? Well, for you guys, this one shouldn't be any problems. How do you find it? You can take the volume and make a derivative out of it. No problem there. What will it be? The derivative AB, and then you'll have minus 4ax 4bx plus 12x squared. So that's the second order equation, and then you just demand, I want him to be 0. Then you find the extreme values, and for this problem here, we should have something, what will it be? Should be something like this, I think. If you have x and volume. So the volume will have a maximum value at some certain x, hopefully. And to find that one, yes, you demand this one equal to be 0, then you should find these extreme values. No questions so far? That's okay. So here I have solved it so far. I have given some numbers for A and B, yes. Here I have my volume function. And then I just invent a whole bunch of x's. I create the derivative as well, the one I have here, plot them and give them a legend. So running this one should then hopefully produce something like this. So the blue one here should be the volume, which then should be part of a third order function. And the maximum value should be here somewhere. Let's see if we can find it. There we have it. X should be 0.23 and the maximum is then 0.3155. That's the maximum volume. And that one now should compare with this derivative equal to 0. And it seems to be quite okay. Yeah, very close to 0 at least. So that will be one way to find the solution, an optimization problem. You simply plot it in MATLAB. And when it is a one-dimensional cost function, just one single x, piece of cake, of course. You can actually do it by hand. If it's a two-dimensional problem, still possible to just plot it and then you can see the solution. If it's 3 or more, you're in trouble. You can't see it, you can't really plot it. So that's where optimization comes in. So how do we find the solution here? Of course, all of you have the optimization toolbox installed in MATLAB. When you install MATLAB on your computer, you should have taken all of the toolboxes. Everybody. That's always nice. Remember, while you're here at the university, you have to steal as much of the software that we have as possible. It's very nice software we have, so definitely steal it. Oh yes. Documentation and then optimization toolbox, and then you can find here toolbox examples. Nonlinear, multi-objective, yada yada yada. So minimalization of a banana function. You have different examples here. Nonlinear optimization. You have unconstrained and constrained. That's mostly where we are going to focus. So I will teach you two functions that you have to learn. The simplest one is called fmean search. In MATLAB, fmean search. That's the simplest one, very simple. Still, it is a multi-dimensional function. So he finds the minimum for a function f who has then n input parameters. And this is actually a very good algorithm. So I don't think you have the source code available. You can see if you can find it on the hard drive, but I don't think you will. So this is closed regard secret. And it's fairly fast. Remember, you have the function f0 in MATLAB. That is part of the standard MATLAB packages without any toolboxes. f0, he can find the function, the zero of a function with only one variable. So he's sort of the cheap one. And he can easily fail if you have played around with this one. You know he crashes all the time. So to use him, you should use him with a function. And then you should give him an interval, find a solution between 0 and 1, then he will succeed. If you give him an initial guess, find a solution in the vicinity of this guess, he will fail sometimes, he will crash. So it's not a good algorithm, but he's free, sort of part of the original MATLAB. F-mean search, that's something else. That's really advanced algorithm. So we talked to Clive Moller, the guy who has been part of making MATLAB, and asked him, couldn't we please have the F-mean search together with the basic MATLAB, so we don't have to pay for the optimization toolbox? And he just smiled, the bastard. So F-mean search, that's a really good program actually, but you have to pay for it. But here it's unconstrained. So here you have no option to tell him x has to be smaller than or bigger than, or x also has to fulfill an equation. Equality constraints and non-equality constraints. That's not possible with F-mean search. So x is totally free. Still, he will try to find the minimum of any given cost function. And normally he will succeed. So that's one function you should know. And you see the syntax, fairly straightforward. I will always recommend this notation here, the syntax. Remember, you are seeking a set of solution here, different x's, but you should also print out fval. What's the value of my cost function for the solution you have found? And even more important, the exit flag. Because sometimes he fails to find a solution, and that's nice to know. Have you found a solution or not? Then you investigate the value of this exit flag. So you find the solution or the information further down here. The exit flag, if exit flag is 1, yes, then he converge to a solution. If it's he is 0, well, he didn't find any solution yet. He just used up the maximum allowed number of function calls. I mean, he has to try and fail a lot here, call this function many times with different sets of inputs to try to find a solution. And then he has a given maximum amount. I don't know how many. It's a part of the input that actually you can change. If it's -1, he has crashed. He hasn't found a solution. So it's only when exit flag is 1 that we actually have a solution. Examples. So here you have the banana function plotted here. There's an anonymous function, and then F-mean search. Find the solution. And you have several examples here. So in our example, I use here the cost function. My cost function is just minus this volume function. And I call the F-mean search here with the function name and initial guess. Try to find the solution around this value. The other function you have to learn about, that is called F-mean con. Now that one is much more advanced. F-mean con is sort of the same philosophy, but here we can have constraints as well. Yep.
Can we specify a range for the solution in?
Can we specify a range? You are thinking about the same philosophy as this one.
Yeah.
So yeah, here. No, I don't think you can. If you look at the help file for F-mean search, you have this x0 which now is just given as where is it? Yeah, it just be a scalar or a vector or even a matrix, but it's not a range. It's just an initial point. So remember, x in general will be many unknowns, 3, 4, 5, 10, 11, I don't know. So the x0 will just be a set of initial values. Try to find a solution around these values, or just a place actually to get him started. Other questions? So actually you can see from the code here, I've done something stupid. I told him with this fmin search, find the solution around 1. But I told him that a was equal to 3, and b was equal to 1. So the maximum value he can have, well, that's 1/2 actually. So I am outside the range already with my initial guess. Of course that can happen if you have some complex equations, some complex constraints. But never mind, let's see if we can find it anyway. Fmin search. The other one, fmin con. Should be here somewhere. Unconstrained, where? Constrained optimization. And there we have fmin con. So again, he finds the minimum of a function with inequality constraints and constraints. And you have also here several simplifications, some possible input when you have very simple constraints. So sometimes you have to program your own additional files. If you have constraints that is somewhat complex, then these has to be programmed. If they are simple, like it is in our case, we have x should be positive and should be smaller than. Okay, then we could use this lower bound and upper bound input directly. The a and b equalities and the c of x, c equalities, yada yada yada. You have some possible input here where you have more or less complex constraint equations. You can see further down for the different examples, and also exercise 5 will give you a test for this one. But now for us, I would choose this very simple form here, or very simple, for the fmin with constraints. So you give him the same cost function that has to be minimized. You give him the same initial guess, the x0. But then I have a equals, b equals, that I don't need. But I want to use lower bound and upper bound, lb and ub. So how do we do that? Well, you can go all the way down to examples. We skip that. I can rather show you, would be easier. Here I have the input. So there you see v2, that's the function call. 1, that is the initial guess for x0. And then I have just empty brackets, empty square brackets. So you have to have then 4 of them, because there were 4 entries that I do not want to use. But you can't just skip them or just say comma, comma, comma. You have to give them an empty matrix, or else he will explode. And then finally, 0. That was the lower bound for my x. And the upper bound should be the smallest one of B half, A half. So now if we run this one, you see I don't have any semicolons behind these, so both of them should print out X, fval, and exit flag. So let's see if they do so. And yes, they do. First, it was fmean search. He reports an X that is around 0.2223, which was quite correct. The fval, that was the value of the cost function, which is my negative volume. So of course the volume is positive. So if I want to know what is the volume for the X I found, well, that should then be the negative of my fval. So the volume is 0.3 something. Exit flag is 1, yes. Then I know he has found a solution. And actually he did then found a solution, even though I asked him to start looking in some place outside the allowed range of X. So that's fairly good. So fmean search, he is normally quite fast. Fast, but does not give you an option for the constraints. For the fmean con, much more complex. He will take longer time to find a solution. But as you can see here, yes, he has found the same solution as fmean search. Of course he has, for this very, very simple problem. The exit flag in fmean con has a whole bunch of entries. So here you can't just check if exit flag is 1 or not. If it's 1, then yes, he has found a solution. 0, he has used up the maximum allowed number of function calls. Negative, he has crashed. But then he has 2, 3, 4, 5. So he has still found possible solutions there as well. So if you use this one, you will use exit flag has to be equal 1. If you use this one, you say exit flag has to be bigger or equal 1 to believe that you have found a solution, to use the solution. You can have some more output here if you like. I believe output, if you also include the output. Let's see what happens. Then you see, to find the solution here, he had to use 6 iterations with a total of 15 function counts. So he found the solution for this problem with only 15 tries. That's not so stupid. I believe he would have used a lot more. Okay, so far the example has been a one-dimensional function. Not so realistic, but just as an illustration. Any questions so far? No? Okay. Let's go to a 2D example. Say you have a region out in the terrain, out in the forest somewhere on the planet. Nobody has been there, so it's a white region. We don't have any map of this terrain. We have no idea how it looks like. And we want to investigate this area in the terrain. We want to find the tallest peak in this unknown area. Find tallest peak in this area. So yes, we will have a two-dimensional problem, and how to find the terrain. Of course, you just hire a plane and you fly over it and take some pictures, and you'll have the geographical data. But say now it's completely covered in fog. You don't see anything, just fog. So how do you do it? Well, you go out and you find yourself a bunch of soldiers, and then you fly over this area and you throw the soldiers out. Should give them a parachute maybe. And then you give them a GPS. And you tell each and every one of them, start walking after you land, start walking and start walking upwards until you can go no higher up. Then he should be on the top. So given that he starts here, and then he should start walking, and then he should stop when he has just look around and see, I can't get any higher. Okay, then I have to be on a peak. And then he phones in the location, and also he can phone in the height of the position that he is located. So this actually is, maybe it sounds a little crazy, but it's not the stupidest way to do things. So here I have constructed a terrain. Just use a whole bunch of sines and cosine. And the elevation, the height, well, that's the yellow and orange colors. So now I just start throwing soldiers randomly in positions and tell them start walking upwards. Of course, several of them will find the same peak. And maybe some of them, they don't even get started. The start will be the same as the stop, pretty much. Let's look at this guy, for instance. He hasn't moved a lot. Doesn't seem to be a peak there. But remember, in 2D, when you have what's called a saddle point, curved this way and curved this way, you will then actually have a location where, when you find or try to find your gradients around you, your surroundings, you don't have any derivatives, you don't have any gradients. So it seems like you are standing on a peak, but you're not. So here you can be sort of tricked, thinking that this is an optimum point, but it may not be. To do this programming here, I did this one very crudely. So here, I mean, I have the function here, sine to the power of 4, sine to the power of 6, cosine power of 2, and so on. And then I just check the surrounding points here around you, and just check whether it goes up or down. Then I have to choose, of course, a quite small delta x to do this. Quite small delta, but that was not a problem. And then if he says no, none of these are bigger than the point that I'm standing, then he reports in, okay, I've found a peak. And of course, then you have a lot of peaks here. So you have to compare all of them. Remember, you were supposed to find the biggest one, the tallest peak. So then you have to compare all of them and then pick out which one is the tallest. And he now returns 24 peaks. The highest one should be at x equals 0.8 and y 0.994. So that should then be this one. Of course, with MATLAB, in a two-dimensional problem, you don't do it like this. You do it like this. You have a rotating option here. And then you easily can see, okay, where's the tallest peak? Oh yes, it's this one back here. So here you can see how these guys have been walking in the fog. Here, of course, you risk missing peaks and you risk missing the tallest peak. If you're unlucky with the position, the random position, you see nobody has found this tiny little peak here. Nobody has found this one, or this one, or this one, or this one for that matter. So several of them is still undetected. So okay, what we could have done here is of course then to increase the number. Where are we? Here we just go to 100. That would be one way to do it. Or maybe we should have done this in an orderly fashion, not use the random initial positions, but have them systematically from x equals 0 to 1 with step of 0.1, for instance, and y from 0 to 1 step 0.1. So do this in a more orderly fashion. Yes, that could be wiser, but you never know. And actually this random idea is normally what you will prefer. So strangely enough, you might say, but it seems to be working quite okay. That is something to do with, let's see, now we found 30 peaks. The tallest one was still the same. And let's see, is somebody still not found? No, yeah, I think he has found most of them. Yeah. Of course, here the cost function that I created has many small local maxima. So I have a whole bunch of peaks. For a real cost function, they don't necessarily have to be so complex. Of course, they can be. They can have a local maxima, minima. We never know. So we sort of have to be prepared for that one as well. Any questions so far? Then we take a break.